Hey everybody. So this is video 2 of a 2-video series in which I'm trying to describe in as simple terms as I can how uh, our misestimate of the normal distribution from the limited information we have from a sample can lead our critical values to shift. Okay, if we're doing a z-test in which we know the population mean and the population variance, the critical values don't shift. They're always the same. But as I mentioned in our last video, most of the things we care about, we don't actually know the population mean or population variance. And so we have to estimate them based on our sample. And our sample will distort our estimates in predictable ways. So go watch video 1 of this series first, and then come back to this one. Because in this video, we're going to talk about how the things we talked about in the last video cause the critical value we need to meet to say that our groups are different or that our group is different from the population is significant. Okay, so I'm going to share my screen and away we go. So first, let's review what a critical value is. A critical value is a value that marks the point at which a value becomes statistically uncommon or rare. All right, and we typically define that as a score that occurs 5% of the time or less. And so a critical value is the value that our difference must meet or exceed in order to be called statistically uncommon or statistically rare. All right, and if it is statistically uncommon or statistically rare, then we often say that it is statistically significantly different from either the other group or the population. All right, now, because of the law of large numbers, which simply says as a sample size gets bigger, the distribution of sample means deviate from a population mean less, and because that also means as sample sizes get smaller, the distribution of those sample means deviate from the population mean more, and we covered that in the last video. Because of that, in smaller samples, extreme values, meaning values that are further away from the population mean, they become more common. Now, because those extreme values, values that differ from the population mean more, because they're more common, we have to look further and further out. We have to look to more and more extreme values before we find one that occurs 5% of the time, 5% of the time or less. All right, and so to illustrate that, let's look at this. All right, so what we have here are 3 distributions. Okay, we have 3 distributions of 100 samples. So let's say we ran with this first distribution. Let's say we took 100 samples of 10 people, and then we mapped the frequency distribution of the means of each of those samples. Let's say we did the same thing here, so we took 100 samples, but let's say that each of those samples were 100 people instead of 10. And then again, we calculated sample means for each sample, and then we plotted their distribution. And this is what we got. And then let's say that we did that again, meaning that we took 100 samples, but this time the sample size of each sample was 1,000. So we've got the distribution of means for 100 samples of 10 each, the distribution of sample means for 100 samples of 100 each, and the distribution of sample means for 100 samples of 1,000 each. Okay, so as I talked about in the last video, you'll note that the peak of the curve is shorter for the distribution of smaller sample sizes than it is for the distribution of larger sample of the distribution of larger sample sizes, and the tails are taller. Okay, now let's look at the same value in each of those distributions. So let's say that our population mean is 80. Okay, and let's say that we want to see whether or not a sample mean of 100 is an extreme score, right? So we want to say, let's say we want to see whether or not a sample mean of 100 is statistically uncommon or statistically rare. Well, whether or not we identified a sample mean of 100 to be statistically rare or statistically uncommon, meaning happening 5% of the time or less, will likely differ depending upon whether we've used sample sizes, whether we're looking at the distribution of the sample means of 100 samples of 10, 100 samples of 100, or 100 samples of 1,000. And we kind of see that here. We might find that in our frequency distribution of 100 of the sample means of 100 samples of 10, a sample mean of 100 happens about 40% of the time. But when we bump up to the frequency distribution of 100 samples of 100, we might find that that same sample mean of 100 is more uncommon, right? It occurs only 20% of the time. All right. Now, how does that happen? Well, remember what we mentioned on the last slide, right? That as sample sizes get bigger, as in shifting from sample sizes of 10 to sample sizes of 100, the sample means of each sample depart from the population mean 80 less. Now what that means is that more of the sample means are going to cluster around the population mean of 80. So this peak is going to be taller. And so all of the scores that could have been out here, they flood in, making a sample mean of 100 less likely, makes it less common. And if we were to bump up again, right, from sample sizes of 100 to sample sizes of 1,000, now a sample mean of 100 is very rare. It happens 5% of the time. And remember, we defined something as we often define something as statistically uncommon if it happens 5% of the time or less. So you see how this same sample mean of 100, right, can be and will be likely considered rare when you have sample means that are bigger than it will be in frequency distributions with sample sizes that are bigger than in frequency distributions with sample sizes that are smaller. Here in this distribution with sample sizes in this distribution of 100, in this distribution of the sample means of 100 samples of 10, a sample mean of 100 happens 40% of the time. But in this distribution of the sample means of 100 samples of 1,000, a sample mean of 100, it only happens 5% of the time. So a sample mean of 100 is statistically rare, statistically uncommon with the sample size of 1,000, but it's not statistically rare or statistically uncommon with a sample size of 10. So with smaller values, as we said, individual sample means in that distribution, the distribution of all the sample means. With smaller samples, the individual samples, they vary widely. And so it flattens out that curve, all right, making bigger or more extreme numbers more common. So, I'll change this here. Maybe it'll help a little bit. Making extreme sample means or large sample means more common, all right? Now, because they're more common, that means the critical value, remember that a critical value is the value that marks the point at which something is uncommon, meaning that it only happens 5% of the time or less. In order to, when we have the smaller samples, because extreme numbers become more common, we've got to move to even more extreme numbers before we find a value that happens 5% of the time or less. So like if we were to go back here right? We already know that a sample mean of 100 is not going to be considered statistically uncommon. So in order to find a statistically uncommon value, we would have to go out here, all right, to maybe a value of 150, right? So the critical value gets shifted further away from the population mean in small values or in small samples. All right. But in larger samples, that happens in the exact opposite direction, such that, well, again, a sample mean of 100 can be considered statistically uncommon when we had a large sample. All right. And so there you go. We have now discussed across both videos how we're having to estimate the distribution of scores based on our sample. And that estimate's going to be flawed in predictable ways. And we've discussed how it's going to be flawed. And we've discussed now in this video how that changes the critical value for determining whether or not something is statistically uncommon or rare. All right. All right, guys, I hope this video and the video that came before it are helpful. And as always, if you have any questions, please send them my way. But if not, I hope you have a great week, and I'll see you later on.